you. So, last time we kind of set the stage and with some background and interesting observation. I hope you found it interesting of screw dislocation, and today we will get down to business and see actual some of our intriguing STM results on bismuth, screw dislocations, and how they can maybe teach us something about the topological properties of bismuth. So this is where I've ended yesterday, the ambiguity or the different possibilities that we see in the literature for the topological classification of bismuth, and the correlated effects that were seen in STM at high magnetic fields in bismuth. Let me start today with a very brief intro to what STM actually measures, so you can really appreciate the data that I'm showing you. So basically what we do is we bring a sharp metallic tip to very close proximity with the surface of the sample, so you can kind of squeeze 1, 2, maybe 3 atoms between the end of the tip, which is zoomed in schematically, of course, here, and the surface of the sample. And this proximity is needed in order to allow quantum tunneling of electrons between the bias tip or the bias sample and the counterpart. So the tails of the wave functions have to overlap through the vacuum separation between them. And what we basically do is use some piezo motors in order to position our tip at a constant height above the sample by monitoring the tunneling current that we measure under some bias voltage that we apply to the sample. So the tunneling current is given by this formula. This is just the finite temperature occupation. For our purposes, we can think of it as zero temperature for the energy scales that we are looking at. And these tunneling probabilities are given by the Fermi-Golden rule. This is basically the density of states of the tip and the sample, and some tunneling matrix element, which is mainly proportional to the overlap of the tails of the wave functions of the electrons, and therefore it is exponentially sensitive to the distance between the two, which gives the very high spatial resolution of the STM method to the topographic features of the sample, for example, the terminations of screw dislocations and atoms. So the resolution is better than a single atom, and to the density of states, mainly of the sample. So here we've already assumed that the density of states of the tip is boring, which we need to make sure it is by preparing, as I mentioned in my previous picture, we prepare our tips on copper samples to make sure that the tips are metallic and nothing interesting happens on the tip side. And the interesting stuff happens on the sample side, which then allows us to take the derivative with respect to the bias voltage, which we measure by differential conductance, which is directly proportional to the density of states of the sample. So at the end of the day, we can take the DC scheme is measuring topography by monitoring the IV current, the integrated density of states, and the differential conductance tells us about the local density of states, energy, and space resolved. So this is the knobs that we have, and let's move to looking at bismuth. Now, actually, the way we ended up measuring bismuth is kind of funny or sad, depends how you look at it. But we were out to measure gadolinium platinum bismuth, which is a magnetic vile semi-metal. But turns out it has bismuth inclusions in it, the way it's grown, in a bismuth flux. And bismuth is much easier to cleave than gadolinium platinum bismuth. So every time we cleave this material, we ended up measuring bismuth. Luckily, bismuth is also an interesting material to measure. So this is basically the data that I'll show you today. It's single crystallites that probably extends over tens of microns, because with the STM we can coarse move over the sample, and it's always bismuth. So these are very sizable pockets of crystallite bismuth. And this is the crystal structure that we expect from the 111 surface termination of bismuth. We can take the differential conductance of the surface. So this is the basically density of states of the surface of bismuth as a function of energy. And this is the very characteristic spectrum, very reproducible. This is the results from Yazdani's work from 2014, if I'm not wrong, where they've seen the 2D TI behavior. You can see the similarities in the spectrum. These were single crystals of bismuth that were cleaved. And we can measure a line cut. So measure the spectrum at every point away from some scatterer in the sample. In this case, it's a crystallographic steppage. This is a bilayer high steppage on the surface of bismuth. So we measure along this cut. This is again the energy spectrum that we see at a single point, and this is the density of states as a false color as a function of energy and distance away from basically the steppage is here, so away from the steppage. And you can see that we get very clear modulations in the density of states, this wave-like pattern which disperses with energy. And this is just an interference pattern that the electrons embed in the density of states as they scatter from, in this case, the steppage. So basically, if we Fourier transform this picture, what we find is dispersing modes, which correspond to scattering wave vectors, which are allowed within the band structure of the surface band structure of bismuth. So electrons from one pocket hit the steppage with a certain momentum. They get scattered into a different state, either within the same pocket of the surface band structure or to a different pocket with a different momentum. And this gives rise to these very reproducible interference patterns, which can tell us something about the dispersion of the material, in this case bismuth. So now let me show you briefly, because we don't have much time, the complex band structure or electronic behavior that we find on the surface of bismuth. This does not relate directly to the topological character of bismuth, but more to the, apparently, the interacting ground state that the electrons assume on this material. Now, the reason bismuth was considered and seen as a material that hosts a correlated surface ground state is because of several ingredients that happen in this material. One of them, it's a very low carrier density semi-metal, so interactions are not heavily screened. And secondly, as I'll show you briefly, there's a degeneracy between three different hole pockets on the surface. So what the electrons basically do due to interaction in order to minimize their energy is pick certain combinations of these three degenerate pockets, which gives rise to these very interesting effects that we don't understand. So I'm showing you the raw data that we've measured. There is not even any symmetrization because we want to see symmetry breaking. So basically, unlike the previous picture that was taken at a line cut away from a stepped scatterer, here I'm showing you scattering in all two surface directions coming from a point impurity of unknown nature that we happen to have on the surface. Most of the impurities that we found didn't give rise to such a strong quasi-particle interference. This is the name of these interference patterns, QPI. But some of them, very few of them, did, and it gave rise to a very large extent of interference patterns. The scale here is 10 nanometers, and a typical separation between atoms is few angstroms. So this is this interference pattern contains tens of atoms. So it doesn't seem to arise from the actual properties of the impurities, but really from the properties of the electronic wave function. So you can see some pattern that disperses with energy, and this is how the Fourier, representative Fourier transform of these patterns look like. And we can basically, okay, one thing we can do is, of course, compare the gamma M direction of this QPI pattern to the gamma M direction that we measured by measuring this line cut from the step edge. And you see the similarities between the two. There are still some differences in the intensities because these are different scatterers. So a step edge scatters more some states, and the point impurity scatters other. This all goes into this matrix element that we didn't take very careful consideration of, but this can give slight differences in intensity, which are quite interesting on their own right. But generally, we see the same dispersion when we look at the gamma M cut, but of course, the point impurity allows us to examine the hole to the band structure of the surface. And basically, this is the pocket structure, surface pocket structure I was referring to. So we have this electron pocket around gamma and these 6 electron ellipse-like pockets at the edges of the Brillouin zone. And then we have these 6 teardrop hole pockets, which play the dominant role in what we see on the surface. Most of the scattering processes we can identify with scattering within these teardrop-like scatterings. And this is a calculation that kind of simulates what are all the possible scattering processes that we can have among this surface band structure. Yes? To P-wave superconductor? D-wave. So no, we didn't compare these. I'm generally familiar with them, but not all the details. But in what sense are they similar? In the symmetry breaking or the general structure? Because what really jumps to our eye is the symmetry breaking. Oh, the nematic behavior, or not that? Well, there have been so many works on high TC, so I'm not even sure to which one you refer, but there could be definitely correlations. One difference, I think, is that always in the case of cuprates, at least, you're in the multiple scattering regime. It's a relatively very disordered material, and this is definitely the other limit of ultra pure material, and we see scattering from a single impurity with no other strong impurities around except the steppages, of course. So we can resolve almost, I should say, and I allude to in a minute why I say that, almost all the scattering processes that we see in the experiment, in the Fourier transform, to the different scattering processes. For example, this ellipse-like structure, maybe you can see them, are coming from scattering within this teardrop, within this teardrop hole pockets. This is this orange arrow, which generates these orange ellipses around the center of the Q space that we measure. So this is nice. We can see kind of a more complete image of the band structure of the surface of bismuth. But now let me focus on the strange things that we see in this image. First of all, the quasi-particle interference patterns are very anisotropic. So generally, you would expect to see all 3 ellipses to look the same and have the same sizes. we can actually extract the sizes of these ellipses, and we see that one direction, the ellipse is much longer than the other two. And if we now trace back the dispersion, so this ellipse structure is basically coming from the wavelength of the electron. We can, by inverting the wavelength to momentum transfer, we can infer also what is the energy separation that we need in order to induce such a difference in wavelength. And what we find is that basically this pocket has moved 4 milli-electron volt higher in energy relative to the other two teardrop pockets. So again, this ellipse shape is coming from scattering within these teardrop pockets. They should all be the same. They are degenerate. However, what we see in experiment is that one of them kind of moved in energy. This is why at the bias at which we measure here, which is very close to Fermi, we see its size becoming larger because its band edge has moved higher in energy, which is exactly a nematic ground state. The definition of a nematic ground state, where the electrons have basically picked kind of a single pocket that they choose to populate over the other two. So this is something we can even trace in energy, and we can even see that indeed two QPI patterns vanish before the third one with energy. So this is one peculiarity that we find on the surface of bismuth, and is actually perfectly consistent, we believe, with what Ali saw before on the surface of bismuth in the presence of a very strong magnetic field. Now we see that it happens also in the absence of magnetic field. So you don't really have to quench kinetic energy with the magnetic field. The interactions are strong enough already for the free electrons on the surface of bismuth. And now let me show you an additional peculiarity which we observe even closer to Fermi. And this time we see it mainly, we can resolve it better in Fourier space. And this is these two additional QPI pockets, quasi-particle interference pockets, that appear along the gamma k direction. And we glanced into this band structure and into this calculated scattering channels for a very long time, and there is simply no possible explanation for such a sharp, well-defined pocket that appears along the gamma k direction. All the teardrop scatterings should appear along gamma m, along these three ellipses that we see in the center. So we speculate, and we really don't have any deep understanding for the mechanism behind that. But one possibility, at least, is that the two remaining bands form a coherent superposition, a coherent ground state. So in the single electron band structure, there is no trace for such a pocket. But if you consider an interacting ground state, and there, of course, the possibilities are vast, you can generate a super position of the two. And now what we image here is basically the scattering between these two new pockets. One support for this is that the shape and momentum position, not direction, but the distance from the center of this new pocket fits exactly what we would expect from inter-teardrop scattering. So before, what we saw around the center was intra-teardrop. If you would consider scattering from one teardrop to the other, you would expect this kind of pocket along gamma m. We see a very similar pocket, but it appears along gamma k. So the surface band structure of bismuth doesn't seem to be a trivial surface state, single electron state. And we don't have full understanding of it. And we cannot rule out that the interacting ground state would somehow affect also the topological classification of it. They can be intertwined, but this is just kind of a taste of the interesting phenomena that we find on the surface of bismuth. And I can only recommend to read also Ali's recent reports on this, which are really showing very accurate and exciting behavior on top of that. So this is what I wanted kind of to show you in a glimpse about the interacting ground state that we find in bismuth. And now, this is just saying the same in other words. Maybe just one last comment. I told you that one of the important ingredients is the low density semi-metallic nature of bismuth. And indeed, if you put in the numbers for this interaction parameter that looks at the ratio between the kinetic energy, Fermi energy, and the typical interaction energy, which is just, this is electron, so it should be not capital E, but the electronic charge over the typical distance between electrons, so this is just a characteristic Coulomb interaction in bismuth, you get a scale of 11, which is not huge, but 1 is kind of the crossover between interaction-dominated material and kinetic-dominated material. So bismuth, the surface of bismuth at least seems to tilt towards the interaction-dominant side, which is kind of consistent with the observation that we have. So it's indeed an interesting material. And now let me switch to talk a bit about the topological properties of bismuth as we understand them. And perhaps the latest evolution in that is its characterization as a possible higher order topological insulator, which means that it's an insulator topologically classified in the 3D bulk, but its surface topological effect happens in 1 dimension, 2 dimensions below the bulk classified band, which means that on hinges, on these edges of the steppages, we expect to see metallic helical modes that reside there. And this is the observation that I showed you also yesterday and in the first slide today that was measured in STM in Princeton of this alternating mode. So this is a differential conductance image, the density of states in real space at the edges of these steppages, and you can see that on one we see some increased density of states, on the other the authors don't, and it's alternating along the edges. And this is a calculation by Andre and Titus of what they would expect from the symmetries of bismuth, mainly the inversion symmetry, which appears in bismuth, together with the C3 symmetry, which is less important as far as I understand. And basically, because these different surfaces have different inversion eigenvalues, you expect to bind helical modes at these interfaces between the different facets. And this is basically a possible explanation for this helical mode, which is observed. So basically, it serpentines along these edges of this nanowire-like shape that is calculated here. And this is how it evolves in energy. So here there's a step edge. This is still data from Princeton. And you can see beyond all this dispersing pattern that we've seen also before, and here it is again in our data, there's also some part which doesn't disperse. This is this red line, non-dispersing line that really sticks to the step edge. This is how it shows up also in our experiment, and there are other reports that see exactly the same thing. This is a very reproducible observation, and the fact that it doesn't disperse really distinguishes it from all these standing wave patterns that we see also away from the step edge. So if it's just a standing wave pattern, it must disperse with the dispersion of the electrons. But if you see something which just sticks to the step edge and doesn't disperse, it means that it's possibly a bound state with some profile, decaying profile away from the step edge. So here we see one segment of it, and we can possibly see a second one also at lower energies. Also in Princeton data, in other reports, there seems to be maybe even another segment of it. So there are edge modes at the step edges or hinges on the surface of bismuth, but this is just cut through them. We can see them on one side and they don't appear on the other side. This is all consistent. But now what we wanted to do basically is test the nature of these edge modes as they face the unique defects of screw dislocation, and more specifically, this, if you remember, as we discussed yesterday, this unique topological kind of step edge that terminates at a point on the surface, and the only way a step edge can terminate on the surface is if it terminates on the surface termination of a screw dislocation. So basically, from this point into the bulk, there is a screw dislocation that goes in. It cannot end. It has to come out either from other surface or create a closed loop. But this one, of course, cuts through the surface, which is why we see it. So the unique thing about it is that this is kind of the only way to put the strongest possible scatterer for this edge mode, because we just terminate the step edge. Otherwise, if it would be a trivial step edge, if it wouldn't end at a screw dislocation, the step edge would just wind around, and then possibly this mode can scatter around different step edges or hinges. Here, it must choose. Either it goes into the screw dislocation, if there's a mode that can support it there, or it scatters back. There's no other way. So this screw dislocation can be either a very convenient metallic channel, helical, topological, for this edge mode, if the topological phase can support it, or it can be the strongest possible scatterer for this edge mode, if it cannot penetrate into the screw dislocation. If it gaps out along the screw dislocation, then the step edge just terminates, and it must gap out towards this screw dislocation. Now, another interesting aspect that we discussed yesterday is that basically this step edge is not really a mathematical 1D object, but it's basically the smallest possible two-dimensional side surface that has two one-dimensional hinges. So this is what happens along this step edge. We have a very tiny side facet, 4 angstrom high in bismuth. This is the height of a bilayer with 2 hinges on top and below, which then terminate at the screw dislocation, which is a truly one-dimensional object. So another thing that the screw dislocation does is kind of collapses this two-dimensional facet into a one-dimensional boundary of the material. So for all these aspects, it's interesting now to go to the experiment and just see what happens to our edge mode as it approaches the screw dislocation. So it's indeed the screw dislocation. This is a strain analysis that we can extract directly from the topography. So if we take the gradient of the topographic image, we can extract the strain which is induced, how much the atoms are pulled, and the screw dislocation applies a pure shear strain. So as you go around the screw, the height of the atoms along the given angle is gradually reducing until by the time you complete the 2-pi rotation, you gather the full Burger's vector, which in this case is a single bilayer shift in the height. So what we see is in the amplitude of the strain is this elliptic-like behavior which decays radially away from the screw axis, which is what you expect for this gradient. You would expect isotropic behavior, but I'll address it soon. And this is the phase of this gradient. So you see indeed, as we expect, that this shear strain winds around the screw axis. So this is the way it points around the screw dislocation. This is this going from blue to black, red, white, and back to blue. So it's a huge strain that the screw dislocation induces, and it's anisotropic. So if we look at the cuts of this quantity along two different directions, you see that the strain doesn't radially relax at the same rate, which was a bit peculiar. For example, at the screw dislocation on copper, they looked perfectly isotropic. But then we also noticed that the bismuth, the crystal structure of bismuth is made out of stacks of bismuth bilayers. However, the stacking is not AAA stacking, but ABC stacking. So also it's not clear how exactly you can induce a screw dislocation, a single bilayer screw dislocation along an ABC stacked crystal, which also puzzled us for some time, because by the time you finish a single rotation, you also have to induce a lateral shift, which in order to connect to the shifted bilayer below, which is very expensive energetically. I mean, the elastic energy you pay for this additional shift of a third of a unit cell is huge. So we were wondering how the screw dislocation even looks like in bismuth, but actually the combination of its anisotropic structure and the ABC stacking probably means that our screw dislocation, the way it penetrates into the bulk, is not normal to the surface, but is along this crystallographic direction, which actually resolves both these observations. So along this direction, there's no problem, there's no such ABC stacking. The crystal is stacked one layer on top of the other, so you can easily induce a screw dislocation. But when you terminate or you cleave the 1-1-1 surface, you indeed get this elliptic-like strain. So basically, we can characterize all the properties of or many of the properties of the screw dislocation. We know its direction. We know the amount of strain it induces. We can calculate in DFT what a uniform such strain would do to the band structure. It's crazy. These are band extrema, pocket extrema. They shift all around. Basically, you can induce just by this shear also different topological phases. This one is definitely in this amount of strain should be a weak topological insulator, regardless of what are the properties of the bare bismuth we started with. So this is the kind of creature that we're dealing with. Any questions so far about the screw itself? So let's move on to measure the spectroscopy. So what I'll show you first, I'll show you two things. One is a spectroscopic line cut that we've measured along this arrow. So it goes along the edge of the step edge, this topological step edge, that then terminates at the screw dislocation and continues on this open terrace until it terminates at this trivial step edge on the other side. So this is the topographic profile that we see along this line. There's also a single missing atom along this step edge, which is another possible scatterer for this edge mode, and this is where we descend by a single bilayer when we go across the screw. And this is the differential conductance, the local density of states as a function of energy and position to the left and to the right of the screw dislocation. So what we see here is our mode. So this is the same mode that we've seen before, the one that sticks to the step edge. This is how it sticks to the step edge along this step. So this is this guy here. On the other side, on the open terrace, we see this region of decreased density of states, which looks like a gap, not a true gap, because this is a semi-metal, but this is basically the gap around the, hidden behind, I have it, the T point of the surface, of the bulk bismuth, which is where this mode is believed to reside. And then we possibly see another faint mode that lives here. I won't talk much about that, but this seems to fit. Let me show this. Maybe you've seen this band structure before. I'm not sure actually in this conference, but this was calculated by Maya for bismuth. And basically this is the T gap, and this is the L gap that we find in this material. And what I want to tell you basically is that this L gap, its smallness, is, we believe, playing a very crucial role in the surface behavior of bismuth. This is kind of the main outcome that we see from this experiment. So we will look at this L gap, but most importantly, what we see is that this edge mode survives very happily down to the last atom where the screw dislocation resides. We don't see any signature of gradual gapping out of it, sensing some strong scatterer ahead of it, which possibly means that it goes into it. Of course, we cannot measure what actually happens on the screw. Unfortunately, I think no one really does. Our ability to probe screw dislocation is quite limited. But out of all the possibilities, what we find is that this edge mode doesn't plunge into the, does plunge into the screw dislocation. It doesn't backscatter from it. So, and now I'll show you a two-dimensional imaging of the whole surrounding of the screw dislocation. 10 minutes, sure, great. So what actually happens as around the screw dislocation, and maybe I'll run it twice. So basically, what you should see here is the mode. So this is a really zoomed in image around the screw dislocation. Its scale is about 5 nanometers. So this is about 10 atoms around the screw dislocation on either side. And what you should see is that there is a mode that runs all the way down to the screw dislocation. I'll run it again. I hope you've seen it. So this is this guy, basically. So this is the energy where we start to see it, and we even see it kind of approaching the screw dislocation. And the reason we think we see these dynamics of the edge mode is basically because of the huge strain which is induced by the screw dislocation. The screw dislocation does change the details of the band structure, of the dispersion. So we believe what we see is kind of a band bending, a slight band bending towards the screw. Really, on the last few atoms, it becomes really huge. And basically then when we go down in energy, we cut this edge mode at different energies, and this gives this running-like behavior as we approach on the last atoms towards the screw. But it seems still to survive all the way down to it. So what could that mean? One possibility is a higher order topological insulator. So this is the cylinder we've seen before. However, what the nanowire-like structure, what we have in our experiment is not a freestanding steppage, but instead this nanowire, this side facet residing on top of a surface of bulk bismuth, which is indeed a steppage. So a steppage, again, is made out of two hinges. So this is the side, 2D side surface, and these are the two hinges that we discuss. which means that basically as far as we understand, we should expect two helical modes that run on the two hinges, separated by this insulating miniature 2D surface. But on the other hand, this is a very clean steppage. So the fact that they are separated only by 4 angstrom doesn't necessarily mean that they have to be heavily hybridized. Of course, if this would be a higher steppage in height, they would be further separated away, and then definitely they wouldn't have to hybridize. But if you're willing to take that these two don't hybridize, although they're separated only by 4 angstrom, once they plunge into the screw dislocation, they really sit one on top of the other. So on the screw dislocation, again, kind of collects this side facet into a one-dimensional object, which means that here they must hybridize. They really sit one on top of the other in real space, and we would expect to see a very clear scattering from one helical mode to the other, and their quasi-particle interference gapping towards the screw, which we don't really see in our measurements. So, looking from the theory side, the only true topological phase which is supposed to bind helical modes on screw dislocations to date is the weak topological insulator. And basically, the screw dislocation, so in a weak topological insulator, it's basically the two-dimensional side facets which carry the helical mode. It's not the hinges. This is a first-order topological phase. So the bulk is a weak topological insulator, which means that the side surfaces of this weak topological insulator should be metallic and have helical metallic surfaces. But then the screw dislocation kind of collects this 2D side surface into a one-dimensional helical mode that can plunge into the material. An alternative view is, again, a weak topological insulator is a stack of two-dimensional topological insulators. So you can think of this miniature two-dimensional side facet as the one-dimensional helical mode that runs around this bilayer, this 2D topological insulator, and then just, let me draw this. So a weak topological insulator is a stack of 2D TIs, and each 2D TI has a helical mode running on its edges, on its circumference, and basically this minimal 2D side facet, which is made out of bismuth bilayer, which was classified as a 2D TI before, is the helical mode of this 2D TI, but then instead of just having layers, we cut halfway through, we shift them, we glue together, and we kind of got a 2D TI which wraps around itself in a loop-like structure, and this helical mode is just kind of winding down along the screw axis until it gets to the bottom surface. So this is the weak TI interpretation. However, bismuth was never in no DFT calculation, and there are quite a few, was never classified as a weak topological insulator. No one identified any weak indices in bismuth. Although it's kind of a natural candidate because we stack bismuth bilayers, which are 2D TIs. So what could be the possible resolution is, again, this is the Brillouin zone of bismuth. These are the high symmetry points around the Brillouin zone. And because it is inversion symmetric, we can simply use the Foucault formula to analyze the topological indices. So the strong topological index is just coming from the band inversion, the parities of all these 8 high symmetry points around the Brillouin zone, which if you multiply them add up to plus. So Bismuth is not a strong TI, and the weak indices are coming from collecting or multiplying these signs along these three planes, which are just normal to the primitive vectors. So it doesn't have weak indices either. So this doesn't seem to support bismuth being a weak topological insulator and any mode plunging into the screw dislocation. However, as we've said before, the L gap is tiny. So if you look at all the ARPES measurements and all the studies, and actually there's even debate about the sign of the L gap, but we're not actually questioning the sign of the L gap. If you just look at the ARPES data, first of all, M is the surface projection of the bulk L point. No one really ever sees the bulk bands around the M point. This is, okay, never mind, let's wait for this. So this is an ARPES study of how bismuth evolves into a 3D topological insulator as it is doped with antimony. Bismuth antimony was the first 3D TI that we came to know. I'm about to finish. So this is clearly has two helical surface bands, and mainly this upper one, called S1, I think, starts from the valence band and terminates at the conduction band that is not really apparent here around the endpoint. And this seems to be a valid helical surface band. In pure bismuth, we see a very similar band, and the whole difference between bismuth and bismuth antimony is whether there was an inversion around the L point or not, which would manifest itself as this mode either connecting to the top of the valence band or to the bottom of the conduction band. It's not a huge difference. You cannot really tell from ARPES measurement what is actually happening. We surveyed all the ARPES data available. All of it looks similar. The M band is never apparent, or the band, the gap around L. But it's, the clear outcome is that the L gap is very small. The possible reason that the bands themselves are not apparent is because a small gap comes with a very large penetration depth. So probably what happens here is that as you approach the L point, or the surface projection of it, which is the M point, the penetration depth of these surface bands grows, almost diverges, and this is why we lose visibility as we approach this point. And it is somewhat uncertain from experiment, and of course it is important to observe that if we would invert our known order of the L around the L bands, we would get a strong topological insulator with weak indices, which would support the kind of behavior that we see in experiment. But actually what we think is that we don't even have to invoke such a inversion or uninversion that DFT never reported and observed. What we believe, and our DFT calculation, current DFT calculation actually support that, is that basically bismuth is is kind of in the critical regime of the topological phase transition. So basically the sheer fact that the L gap is so small means that the topological properties kind of start to emerge out of, on the surface of bismuth. And here I'm showing an interesting study done on bismuth selenite or some variant of bismuth selenite as it is doped with sulfur. So bismuth sulfur is not a 3D TI, bismuth selenite is a 3D TI, and the transition happens around a concentration of 0.5 doping. So in 0.6 level doping, these are the Dirac surface states, the fully formed Dirac surface states. With very low doping, we see insulating behavior, but as you approach the topological phase transition, the closing and reopening of the gap, what you see is not only the bulk gap is closing gradually, but also surface bands which are practically helical start to be induced, kind of are pulled out from the bulk or highlight, increase intensity from the bulk as the gap gradually closes. And this is kind of the critical, approaching the critical region of the topological phase transition. And these bands are not topological. You know, their topological classification is trivial. However, they have almost all they are practically helical. If you would induce superconductivity, you would get, I believe, should be tested. I believe it is being tested. Should get Majorana edge states from them. Being approximately helical is good enough for that. So basically, what we believe happens in Bismuth and all the surface and edge modes that we see are not really bands which are related to a weak topological insulator, because we do believe that Bismuth is not. We believe the DFT calculation, but the L gap is small enough for Bismuth to be in the critical region of the topological phase transition, and therefore we see approximately helical modes that do, to large probability, enter the screw dislocation because they are practically helical. So this is our current understanding of our observation on Bismuth. And then again, it may be that the correlated state also is part of the picture. We have no idea how these two combine and what stands behind of that. Let me just put on a last slide to advertise that we'll have a completely different topic, or maybe not completely different, because Bismuth may be also part of that, but we'll hold in the Weizmann Institute school about electron hydrodynamics. Part of it would be about electron hydrodynamics in topological materials, a lot also in graphene. So you're welcome to apply. It will be held in January next year. Thank you very much.
Time for a couple of questions.
Yeah, thanks for the presentation. I was actually missing a point on the 2 slides back. You showed the ARPAS data, and you mentioned that at the endpoint you cannot observe any bands because you said there's a large penetration depth because the small gap opened. But I kind of missed the point of why bands are not observable anymore.
Okay, so one observation is that if you go through the literature, here you should observe these two surface projection of bulk bands, which are the bulk bands at the L point. They are never observed. Now, when you have a small gap, the penetration depth is inversely proportional basically to the size of the gap. So in a true insulator, you can get tightly bound surface states as you close the gap. This is basically what happens in a vial semi-metal. Maybe this would be a more familiar picture to this audience. So as you go closer on the Fermi arc, as you go closer to the vial node, the vial cones are gradually closing, and therefore the gap is reducing, and with it, the penetration depth of the Fermi arcs is diverging. It's exactly the same argument. How much the surface band penetrates into the bulk is inversely proportional to the bulk gap it sits on top. So what ARPAS measures is, of course, the surface band structure. It has some penetration into the bulk. And one possibility, at least, is the reason we don't measure it, but no one observes any band around M, and this is Zahid's data from the first, this is bismuth antimony. Again, these are just DFT lines added on top of the ARPAS image. There's nothing there behind in the data. No one sees the L bands. So it's hard to say something on them from experiment. We have DFT. And there are ways to assess gaps in DFT to high accuracy, and all of them agree that bismuth is not a weak TI, that the L gap has the parity that it claims to have. But the size of the gap should be around 13 milli-electron volts. So it's really a small gap.
No.
So I'm way more in thin films than in single crystals. But I know in thin films sometimes if we see a screw location, we see like the growth continues at the screw location specifically and not the film itself.
Right.
I don't know exactly what's going on with the dynamics behind this, but I was wondering, do you maybe in single crystals also see these pillars kind of?
So Leslie was added. If I go back to the first slide, I'm not sure how valid this is for pure bismuth, and maybe Leslie can say more. But if you Google bismuth, this is the kind of crystals that you find. And you can really follow this screw-like structure with this chirality all the way until it terminates with the opposite chirality. And there is a notion which is called screw dislocation-induced growth. So you can use it to induce growth. And mainly when the material is very anisotropic, then the atoms prefer to stick on the sides of the 2D films and they don't get stuck on they diffuse freely on the surface. But then if you have a screw, then you kind of can seed perpendicular direction growth. So it's known for chemists, and they even sometimes use it as a method. So.
Andre, you had a quick question when
In your hexagon, why would you have the termination where the escape goes back?
Because as far as I understand, and if this is wrong, I'll be happy to not write. It's very small. You mean here? This guy?
Yeah.
So basically, this surface and that surface are identical, are the same termination of bismuth. So we would expect that they would have the same inversion eigenvalue. What? Yeah. Yes. So, yes. Although there is a caveat, because the unit cell, I'm not sure it's really, there is this observation, for example, in tin telluride of edge modes on step edges, and they are explained by a partial unit cell shift. Now, bismuth has this ABC stacking, and this is a single bilayer step. So I'm not sure if this means it's a third of a unit cell step, which means that these are not identical surfaces. But on the other hand, you can define different primitive cells that have only a single bilayer, and then this would be definitely the same surface termination. But simply speaking, I think they should be the same.
So I invite you to ask further questions over lunch. So let's thank Haim.